All right, 7.6 is kind of what we've been working towards this entire chapter. Really, all of the other sections, we've kind of been picking up tools along the way. We've been learning how to add and subtract, multiply and divide with these rational expressions. We've been learning about complex fractions in 7.5. What do we do when we have a fraction in a fraction or multiple fractions in a fraction? And all of this stuff paired with the Chapter 6 material on factoring and foiling and all that jazz is really what we've been working towards to get to 7.6. 7.6 is where we're really going to start solving things. Almost every other section, even if it said solve, we didn't actually find out what the variables were. We maybe just simplified till we couldn't simplify any further. And so today we're actually going to be able to figure out, what does this variable equal? And so when we solve rational equations, there's a couple of different things that we're going to have to do. And there's one specific thing that we have to do at the end that's a little bit different than we've had to do like with regular equations. So the first thing you want to do is you want to look at the denominators of all of the fractions involved in the problem and find the least common denominator for all of those. You're always going to do that. It's going to simplify your life straight out of the gate because after steps 1 and 2, we will no longer have fractions and it makes our lives a little bit easier. Now, that doesn't mean you won't end up with a fraction as your answer, but you don't have to play with fractions the whole time. And so, in general, that usually makes it easier. So find the LCD of all the fractions involved in the problem. Then you're going to multiply both sides of your equation by that least common denominator. Step 2, I would say, is where most people go wrong. Not because it's a hard step, but a lot of times we have constant terms as well as our fractional terms. And when I say we're going to multiply both sides by the least common denominator, we're multiplying absolutely everything by the least common denominator. And that includes any and all constant terms. And I will say almost every time a student comes to me and tells me they got the wrong answer, I look and they multiplied their fractions by the least common denominator, but they didn't multiply that constant term, and obviously that messes up the problem. So step 2, multiplying both sides, means you're multiplying every single term by that least common denominator. So step 3, we'll remove any parentheses and combine all of our like terms. Step 4, we solve. And step 5 is that extra step that a lot of times is included on these how-to solve different like step things where we check our solution. And 99% of the time we never check our solution because, especially in lecture, you guys just trust me, which is risky. But in general, you don't want to go through and rework the problem by checking your solution. And I understand that. And check your solution usually is, like a little nudge that if you have time, you should always check your solution. Rational equations, you always want to check your solution. I'm going to show you a couple of examples, or at least one, in the notes, and I know it comes up in your homework as well, where when you do rational equations, you can get what's known as an extraneous solution. And an extraneous solution is a solution that comes mathematically out of the problem, just like any other solution. But when you plug it in, it does not work. I'm going to show you how to look for these, and I'm going to show you how to easily spot them so that you don't necessarily have to always plug in the answers. But your best bet, in the way that I do it in the homework and in the notes, is I always check my answers over to the side. So you want to get in that habit with the rational equations, but I am going to give you a helpful hint on what to look for to help you identify these extraneous solutions. So step 5 in this case is not really a suggestion. It really is something you want to do. Are there any questions about any of these steps before we try the first problem? Okay, first problem, we have t over 4 minus t over 5 equals 1. We need to find the least common denominator between 4 and 5. And here's something to note. While these how-to steps say least common denominator, if you find a common denominator, it will still work. You just usually have more simplifying later on. But I do want you to know that you don't have to sit and struggle through necessarily, because one way you can find a common denominator is always to multiply your denominators together. In this case, 4 times 5 is 20, which is our least common denominator. But even if it was just a common denominator, multiplying everything by that will still get rid of your fractions, and it will still give you a simpler problem. You just might have a little bit of reducing later on. So just know you can find common denominators or least common, whichever way works. So in this case, I'm not trying to get my denominators to 20. I'm going to multiply every single term by 20. So I'm going to take 20 times t over 4 minus 20 times t over 5 equals 20 times 1. Every single term in the problem gets multiplied by that least common denominator. Every single one. Not trying to get the denominators to that, because if I get the denominators to 20, sure, I can combine them, but then I still have to play with fractions the whole time. Does that make it wrong? No. If you're confident with your fractions, you can totally do that problem that way. I teach it this way because we get to get rid of those and we don't have to worry about them. Because later on, as our denominators get more and more complicated, it's easier just to get rid of them than it is to play with them. 20 is the same thing as 4 times 5. So notice here, when I do this multiplication, I have a 4 on top and a 4 on bottom. I'm simply simplifying on the front end. 20, as I just said, is 4 times 5, so I have the 5s cancel on that one, which means I'm going to have 5t minus 4t equals 20. So t equals 20. Step 5 says I want to check that, so over on the side I would do the check. And the way you check is you put the solution you got in place of the variable in the problem and make sure it works mathematically. 20 divided by 4 is 5, 20 divided by 5 is 4. Hey, that does equal 1. We did check. It does work. So t equals 20 would be the only solution for this equation. Questions? Okay. For B, we're going to have x minus 2 all over 12 equals 1/4 minus 2x minus 1 all over 3. This one's slightly more complicated than the first, as they will continue to get, because our numerators, we get a little bit more complicated up there, but our denominators are still single numbers. So I need to find a least common denominator between 12, 4, and 3. Yeah, 12 is the least common, because 4 times 3 would give me 12, 3 times 4 would give me 12, 12 times 1 would give me 12. So 12 is my least common denominator. Again, if you don't see that, you can take 12 times 4 times 3. Obviously, you get a large number at that point. It'd be 144. But algebraically, it would still end up giving you the same solution in the end. And maybe you wouldn't need to go up that high. Maybe you would think, oh, 24. I know 4 goes into 24, 3 goes into 24, 12 goes into 24. That also works. But if you spend the time finding the least common, you have less to do later on. So nothing else changes. Even though the tops are a little bit more complicated than the bottoms, I'm still going to take 12 times every single term in this equation. And then I will choose to do my simplifying on the front end before I do the multiplying. For that first fraction on the left-hand side of our equal sign, I would have a 12 on top and a 12 on bottom. So they're going to end up going away. The next one would be 12 times 1/4. Well, 12 is the same thing as 4 times 3, so notice there would be a 4 on top and a 4 on bottom. 12 is 4 times 3, but this time there's a 3 on top and a 3 on bottom. So that leaves me with an x minus 2 on the left equals, nope, not 4. 4 canceled first. So it'd be 3 minus 4 times 2x minus 1. So step 3 says remove parentheses and combine like terms, because this is what's going to happen as our numerators get more complicated. A lot of times we will be left with a situation where we have to get rid of our parentheses using our distributive property. So I'm going to distribute the negative 4 to the 2x, giving me a negative 8x. Distribute the negative 4 to the negative 1, which gives me a positive 4. The sign goes with the number. So if it's a negative, the negative comes in. If it's a positive, the positive will come in. Now I'm going to combine like terms. On the left-hand side, I've got nothing to combine. But on this right-hand side, I have a negative 8x, and I have a positive 3 and a positive 4, which will give me a positive 7. At this point, I have x's and constants on both sides. It does not matter which way you take your variable. You just want to make sure you get your variable all on one side and you get your constant terms all on one side. In general, I will typically take my x's wherever they're going to stay positive. So I only have one x on the left and I have a negative 8x on the right. So if I add to move that 8x over, that's going to make my x's positive. So that's in general what I like to do, just so I don't have to worry about accidentally dropping a negative somewhere. Add the 2, get 9x equals 9, divide both sides by 9, x equals 1. Now again, our last and final step is always to check. So you're going to want to check, and the way you do that is you plug 1 in for x everywhere at the beginning in the initial equation. So instead of x minus 2, you'd have 1 minus 2 over 12 equals 1/4 minus 2 times 1 minus 1 over 3. Gross. It's still going to have that fraction, but that's okay. Because what I'm going to end up doing is multiplying by the least common denominator to get rid of that fraction. It's 2 minus 1 up here on top. So that'd be a minus 2 minus 1, which is 1/3. Don't worry, I'm going to give you guys a hint here in a minute that's going to help us not have to do this quite so often. Negative 1 equals 3 minus 4, which does check out. So far, all of these have worked. And like I said, I'm going to show you a hint or a tip here in a minute that's going to help you identify the extraneous solutions to where we don't necessarily have to check every single problem. But it's not a bad habit for you to get into checking the problems, especially if you have time. Are there any questions on the first two? Okay. Let's stick a variable in our denominator. Make it a little bit more complicated. In case you needed those steps, I'll leave them up there for the next one. We have 4 minus 5 over x equals 3/2. So we have a constant term, we have a term with a variable in the denominator, and we have just a regular old fraction. Regardless, we're still going to ask what's the least common denominator amongst our denominators. Well, We're getting there. 2x. So remember, if we're not sure, and especially if there's a variable in the bottom, you just multiply those denominators together to give you a least common denominator. 2x will be our least common denominator. Which means nothing changes in how I'm going to do this problem, except now I'm going to multiply every single term by 2x. So I'll take 2x times 4, 2x times 5 over x, 2x times 3 over 2. At first term's a constant, so nothing's going to cancel out. There was no denominator for me to do anything with, so it's just going to become 8x. The 2x times the 5 over x, notice there would be an x on top and an x on bottom, so those go away. So I end up just multiplying 2 times 5. There's a negative in front of there, though, so it does become a negative 10. And then on the other side of our equal sign, I have 2x times 3 all over 2, so notice there's a 2 on top and a 2 on bottom, so I'm just taking 3 times x. Now we've got to get all of our variables together, get all of our constants to the other side. I know there's an x on both sides, but like I said, I like to keep my x's positive if I can. So I'm going to choose to subtract the 3x to move it over. So I have 5x minus 10 equals 0. Add the 10 to move it over. So you have 5x equals 10. Divide by 5. X equals 2. Now, this is, again, we would check our answer. In my handwritten notes, I do check it. It does work. This is actually the first problem, though, where we potentially could have had an extraneous solution. Here's why. Your extraneous solutions are going to pop up when you have a variable in your denominator. When I teach this in my college algebra class, we call them extraneous solutions because that's what they are, but I also just in jest call them the trouble spots, because what ends up happening is there's a special thing that can never be in the denominator of our fractions. Does anybody know what it is? What can never be there? Zero. We can never divide by 0. It causes all kinds of problems. That is always true in math. I don't care what level you're at. You don't divide by 0. And so when we have variables in the denominator, theoretically I could say, well, let's let x equal 0. If x is 0, that causes a problem. If we think of our equation as a machine, we put 0 in, our machine breaks. Like it stops working. And so, but what happens if I were to do all this math and I get x equals 0 at the end? That's going to happen. There's going to be times where I did all of this math, and then I get down here, and it's like x equals 0. But if I put 0 in, it breaks my machine. So even though algebraically I found 0, if I plug it back in, it's going to break it. Then I would say I had no solution, because the one solution I found was extraneous. Now, I say that with warning. It's not always the number 0. Yes, 0 in the denominator is what always breaks the machine, but as we will see, I think in the very next problem, our denominator isn't going to be just an x. Our denominator could say p plus 3. Well, 0 is not going to break that machine then, because if I have p plus 3 in my denominator, if I plug in 0, the denominator is 3. That didn't break my machine. It's whatever value makes your denominator equal to 0. That's what breaks your machine. And if you mathematically find that as your solution, then it will not be a solution in the end, because that's an extraneous solution. We will have that coming up on one of our problems. Okay? So really, the only ones you have to check are when you have a variable in the denominator. That's when it's easiest to say right at the beginning. Like when you find your LCD, you could note your trouble spots. You could say x cannot be something. And you could look. Well, x cannot be 0. So then when I find my answer is 2, hey, that's okay. I just couldn't let x be 0. So I know this is a solid answer. I know I'm good to go. If I found 0, and I had already stated that x cannot be 0, then I know that there's no solution and there's a problem. Give me a minute and you'll see it. We're going to have a problem like it because you have a problem like it in your homework. Are there questions on this one? Okay. We got some more coming. Here's D. D is P minus 5 over P plus 3 equals 1 over 5. I put this problem specifically in the notes because we can actually do this problem in a completely different manner than our 5 steps. Does anybody have a wild guess on the way that we could actually solve this? And it's okay if you don't. Here's a special note. If you have a fraction equal to a fraction, just a single fraction equal to a fraction. None of our other problems have been a single fraction equal to a fraction. We've had a constant or something like that. But if you have a fraction equal to a fraction, you can cross multiply. Cross multiply, butterfly multiplication. I don't know of any other terms that people have had with that. But you see this in Math 20 in 2.7 when we talk about ratios and proportions. Because what we end up doing is we set up, this is basically a ratio or a proportion, and we can solve by cross multiplying. That means we take the top of the left times the bottom on the right. So it'll be 5 times P minus 5. And we set that equal to the bottom of the left times the top on the right, which would be 1 times P plus 3. We've eliminated our fractions, all in that one step. So I'm going to get rid of parentheses by distributing the 5, so that I get 5P minus 25 equals P plus 3. Subtract the P. I'm going to do more than one step at a time here, because I'm going to move my variables to the left. I'm going to move my constants to the right by adding the 25. You can make that into 2 steps as we've done before. I'm going to do it all at once just to save some room. That'll give me a 4P equals 3 plus 25 is 28. Divide by 4. P equals 7. Now, we didn't actually list out any of our trouble spots or what P could not equal at the very beginning. So if we don't figure that out, then we would have to plug 7 in and make sure it works. But really, when I'm trying to figure out what my trouble spot is, all I care about is my denominator that had the variable, P plus 3. I do not want that to equal 0. So I'm going to set it equal to 0 to figure out when that happens. I subtract the 3, subtract the 3. When P is negative 3, that's when my denominator equals 0. I didn't get P as negative 3, though. I got P as 7. So this is a solid answer. This is good. We don't have to worry. It's not an extraneous solution. We're good to go. So if you have a fraction equal to a fraction, you don't have to worry about the least common denominator. You can simply do cross multiplication to get rid of your fractions and then solve. Yes.
On C.
On C, yes. Up here.
Yeah.
Okay.
If we made our the 4 will want to cross multiply that?
No, because it's not a single fraction equal to a single fraction. We have 2 fractions equal to a single fraction.
Oh.
If you spent the time to make all of this into 1 fraction, then you could, but honestly, you're making a lot more work for yourself. Good question. It has to be 1 single fraction equal to 1 single fraction to do the cross multiplying. Other questions? We'll do another one, just like it. E is 9 over x plus 1 equals 5 over x minus 3. We have a single fraction equal to a single fraction, so we can do cross multiplication. But I am going to go ahead and figure out my trouble spot or trouble spots first, so that as soon as I find my solution, I know whether or not it's a good one or not. So in this case, we have two denominators that are different. They both have variables, so I would set each of these equal to 0 to figure out what my trouble spots are, where my extraneous solutions would be. I would have x plus 1 equals 0, and I would have x minus 3 equals 0. Subtract the 1 so that I find x is negative 1, and add the 3 to find x is positive 3. If I get either of those answers out algebraically when I'm working this problem, I know I've got a problem. If I get any other answer in the whole world besides negative 1 and 3, I'm good to go. So far, we haven't had any extraneous solutions. So far, they've all worked nice. So I'm going to take 9 times the x minus 3 equals, and I'm going to take x plus 1 times 5. Cross multiplied, I get rid of my fractions. Now I'm going to distribute. 9x minus 27 equals 5x plus 5. I'm going to move my variables to the left, my constants to the right, just so I can keep everybody positive. Divide by 4, and I got x is 8. And I know that is a good answer. It works because it's not x equals negative 1, it's not x equals positive 3. Any questions? Okay. Let's look at the next one. The next one's fun because the next one we get a new special trick too. I'm all about the little tricks. (3x plus 4) all over x plus 5 equals 2x minus 1 all over x plus 5. What do you notice immediately about this problem? The denominators are already the same. And here's something that's really nice. If your fractions, if every term in your problem already has the common denominator, you can ignore them. They go away. Because here's what happens. If I were to do cross multiplication at this point, notice I would have an x plus 5 on both sides of my equation. That's multiplying by something, which means I would divide both sides by those x plus 5s, which means they go away. So I'm going to write the note down that I've just said, that if the fractions or all terms have the same denominator, you get to ignore them. So instead of thinking of this problem as 3x plus 4 over x plus 5 equals 2x minus 1 over x plus 5, I get to just think of it as 3x plus 4 equals 2x minus 1. The bottoms completely go away. I get to ignore them. I don't have to worry about them. I just get to solve. So I'm going to subtract the 2x, subtract the 2x, subtract the 4, subtract the 4. So I get x equals negative 5. Now, the original problem, my denominator, was x plus 5 on both of them. If I set that equal to 0 and subtract the 5 to move it over, it tells me that if I let x equal -5 and I plug that back in up here, my denominator goes to 0. This is one of those times where we have a trouble spot at the same answer we just got. Mathematically, we found the answer is -5. But if I plug -5 into my problem, my machine breaks. So we can't let x equal -5. So in this case, we would say there's no solution. The one solution we mathematically found was an extraneous solution. It doesn't work. So even though we found an answer, it ends up breaking our machine, so we can't use that answer. So we would say that there was no solution. On all of your homework problems, you're given 2 options, I think at least 2, where you're allowed to type in your answer, or you can select that there is no solution. And this is the first case you've actually had where this happens. Are there questions on the extraneous solution, the no solution, or any of that? All right, we got one more to do. I mean, I have lots more because I have all the homework problems too, if we want extra. But I've got one more in the notes. Yep, that's a plus. Finally get some binomials and things down there in our denominators a little bit. All of your chapter 6 stuff is key for this section, for this whole chapter.
Should that be a W squared instead of x?
Yes. It should be, thank you. I always go to x on default. I even did that in some of the the problems when I went back to Pearson. I would type in x whenever I needed to simplify a problem, and they're like, your answer's wrong. I'm like, oh yeah, because you used a W or you used a Y. That's why almost always on my handwritten tests, I end up using X just to keep it simple. Okay. This one obviously has the most complicated denominators that we've seen, but they're still not super complicated. Here's a good rule of thumb. Whether you have, this one's a difference of squares situation here. Whether you have a difference of squares or you have a full-blown quadratic polynomial down there, like x squared plus 2x minus 1 type situation. Whether you have something like this or even the trinomial that I just mentioned, odds are the other denominators are the factors of this one. And in this case, that's exactly what happens. Now, that doesn't always work out perfectly, but odds are at least one of the other denominators will be one of the factors of the factored trinomial or the factored quadratic. So I tell you that to look for that, to help you find the least common denominator. Because this is a difference of squares, which factors into w minus 2, w plus 2. So that's what this denominator is. This denominator is w minus 2. This denominator is w plus 2. That means my LCD is going to be the w minus 2, w plus 2. That's what I'm going to multiply every single one of my fractions by. But before you freak out and think, oh my gosh, that's a lot of foiling and stuff we're going to have to do, you're really not, because most of it's going to cancel away. So I'm going to take w minus 2, w plus 2, times the 5w over w minus 2, w plus 2. And I usually write it out in the factored form like that in the bottom, because then I'm going to see how everything's going to cancel out. Plus w minus 2, w plus 2, times 1 over, I'm going to run out of space, w minus 2. So I'm just going to come down and put equals w minus 2, w plus 2, times 4 over w plus 2. I had to come down a little bit because I should have turned my paper the other way. So for that first fraction, the 5w1, notice the top and the bottom share both of those factors. That means it's going to leave you with 5w. I keep putting equals, and that is going to be a plus. Now, for the 1 over w minus 2, the denominator is w minus 2, so that's going to cancel with the top w minus 2, leaving me with just a w plus 2. Equals, and then on the other side, my denominator is a w plus 2, so that cancels with a w plus 2 on top, so I will have 4 times w minus 2. We still have some work to do, but it's not as complicated as you think it's going to be because we don't have to do lots of foiling and factoring and all that kind of jazz. On the left-hand side, I'm just going to combine my like terms so that I have 6w plus 2. On the right-hand side, I'm going to distribute my 4. So 4w minus 8. I'm going to keep everything positive, so I'm going to choose to subtract my 4w and subtract the 2. So I move all of my variables to the left, all my constants to the right. That'll give me a 2w equals negative 8 minus 2 gives me a negative 10. Divide by 2. Find my w is negative 5. Now, in order to make sure that that actually works, you have two options. You can plug that into the original equation and make sure that it works, or you can find the trouble spots from the original equation and make sure negative 5 was not one of them. The trouble spots are anywhere the denominators would go to 0. Well, my denominators were w minus 2, w plus 2, and this one was a combination of them. So really, it's w minus 2 and w plus 2. So the only time my denominators would go to 0 is when w equals 2 and w equals negative 2. That's when my denominators go to 0. That's when my machine breaks. But I found w equals negative 5. So we're fine. That doesn't produce an extraneous solution. It doesn't give me 0 in my denominator. I am good to go.